Hi y'all. Today we are learning exponent rules. To start, I have a little bit of a review here. Ms. Joelle told me that you learned how to change fraction exponents into radicals. So this will be a little bit of review. That's method one. And then I'm going to show you a different method that you might like. So you have the two, remember you move it out and it becomes the index of your radical. So we have the square root of 36, which you know is 6. So something to the half power is its square root, right? Same deal is happening here, like with 27 to the 1/3. We would have 3 swinging out to become the index. So the cube root of 27, which is 3 times 3 times 3. So I know the cube root is 3, like that. So anything to the 1/3 power is the same as a cube root. So you probably remember at least a little bit of method one. Method two is a different method. So it's to break it into parts and then choose the right number. So basically what I'm saying here is when you have 36 to the 1/2, you're breaking it into two parts. So you're essentially saying what times what gives me 36? Well, and it has to be the same number. So I know it's 6 times 6. And then this number here tells me how many to choose of them. I'm going to choose one of them because it says 1. So this is your how many. So my correct answer is 6. You can see you get the same thing. This is just breaking it into parts, right? So here for 27, this is how many parts. So I need 3 parts that multiply to get 27. That'd be 3 times 3 times 3, and choose one of them. I'll choose this one, doesn't matter. Um, and I have 3 there. So you see the same method here. I think that method two becomes more helpful when you have a number that's not 1, right? If it's not just like a standard half power or third power. So for example, this one here, if we're going to change to a radical, you would take this, move it out in front, and say, okay, square root of 36 to the power of 3, because I still have that 3 there, so that 3 is sticking around. So this would be square root of 36 would be 6 to the power of 3. 6 times 6 times 6, 216, like that. Here for 27 to the 4/3, I would take this thirds, move it out here. This is the cube root of 27, still to the 4th power. So cube root of 27, remember that is 3 to the 4th power. 3 times 3 times 3 times 3 is 81. Right, so this is probably the most traditional way of doing this type of problem. If you'd like to try the other way where you're breaking it into parts, then basically this one's still telling me how many parts. So 36 broken into two parts. It says 6 times 6. And then it's saying how many of those parts do we need? We want 3 of them. So I'm going to add or multiply a third part here. 6 times 6 times 6 is 216. Right, so you can think about it in a slightly different way, get the same answer. Same thing here. So 27 broken into 3 parts would be 3 times 3 times 3. And in this case, we want 4 parts. So we're going to multiply a fourth one. 3 times 3 times 3 times 3 is 81. So 2 separate methods showing the exact same way. Okay. We're going to play a game today. So if you're in class, we'll play it together. Cool. Now we're going to get into some like nitty gritty exponent rules. You probably remember these. We're going to do slightly more complicated examples, but you should remember the rules from Algebra 1 and from Algebra 2. So a to the m times a to the n. If we have the same base, so the a's, and they're being multiplied together, then we are going to add the exponents. So this would end up simplifying to a to the power of m plus n, like that. So if I have a complicated example like this, I have the same base. So I know that they are going to have the same base here. And then I'm going to add my exponents. Notice I'm adding 2 binomials here. So I'm going to add 2x plus negative 4x would be negative 2x. And then negative 3 plus 5 would be positive 2, like that. There is a negative here. We'll deal with that later. But for now, this is as simple as we need to go. So they're being multiplied, so we add exponents. Right? That is our first rule, right? Our first rule. All right. Our second rule is this one here. If we have the same base being divided, we're going to subtract the exponents. Right? So this, if it's a to the power of m over a to the power of n, we'd have a to the power of m minus n. So we have whatever this is, we're subtracting this one here. So if I have this example here, I see that I have division, but before I can even get to the division, I need to do this multiplication. So I'm going to use my rule from above where I am adding the exponents here. So I have 2 to the power of 1x plus 3x would be 4x's plus 4 over 2 to the power of 2x plus 1. So I'm just applying that rule from above. And now I'm going to go ahead and do my subtraction. One way that I might write this is just like subtracting 2x plus 1, like that. I'm basically taking this and just moving it right here. Right? That way I don't have to like keep writing it over and over again. So all of this is now up there. So my answer would be 2 to the power of 4x minus 2x would be 2x. 4 minus 1 would be positive 3. So this is the simplified version of what we started with here. All right, so for this rule, if we have division, then we know our exponents are being subtracted. The next rule is called power of a power, right? And when we have power of a power, we have a power to the power of another exponent, right? So this is a to the power of n to the power of n. So this would be multiplication, a to the power of m times n, right? We multiply the exponents. If you're having a hard time thinking about this, think about like x to the power of 2 to the power of 3. There are 3 x squareds. So we'd have x squared times x squared times x squared. X squared times squared times squared, that would give you x to the 6th. We could have skipped all those steps by doing 2 times 3 to get us to here. Okay. So if we have a power and a power, we're going to multiply. Notice that this is different from this first one here where we actually had the multiplication symbol. That's because the base is, there are 2 separate bases here. Here we only have 1 base. So for multiplying here, we see the 2 to the power of 3 to the power of this. So we have 3 times x minus 2. So we're going to be multiplying. That requires distribution here, like this. So we would have 2 to the 3x minus 6. The rest of our problem reads this here. And then we're applying that first rule since they have the same base. We can combine them using addition of the exponents. So I have 3x plus negative 2x would be just positive x. And then negative 6 plus 2 would be negative 4. So this is the simplified version of all that. All right. Cool. For the next one, we have a negative power. So we have a to the power of negative n, right? The colloquial way I would say this is just flip the fraction, right? So since this is technically on top, right, it's going to move to the bottom. It's going to become 1 over a to the n, right? Notice that negative drops off and it moves to the bottom of a fraction. If it was already negative on the bottom, so if we had like 1 to the power of, call it x to the negative 4th, then it would be moving up to the top and it would simplify as x to the power of positive 4, right? So the negative basically just lets the numerator become the denominator, or whatever's in the denominator move into the numerator. So if I'm thinking about this one here, I have 3 to the power of negative 2x plus 2. Note that this one is negative, but this one is not. So I'm going to need to factor out that negative first. So this is like 3 to the power of negative 2x, but also minus 2, like so. If I multiplied this negative back in, it would create this here. So I know that these are equivalent. So now, since this is negative, this whole power is negative, that means that it can move to the bottom of a fraction, become 3, the 2x minus 2 over 1, like that. This is we want to get rid of the leading negative, right? So yes, there is a minus in here, but we want to get rid of the leading negative. So this is technically the simplified version of this here, right? Remember all 3 steps, this step, the yellow step, the green step, and this red step here. All 3 of these are equivalent, just writing them in different methods. All right. You may have remembered this one. This is usually my students' favorite one. Anything to the power of 0 is positive 1. If you think about the division rule, let's say you had a 7 over a 7, right? You might automatically be like, well, anything over itself is 1. That's true. We can also apply that division rule, a 7 minus 7. That would be a to the 0 power, right? So anything to the 0 power must be equal to positive 1. Let's see how that applies here in our example. So for this example here, I need them all to have the same bases. The first thing I can do is change 4 into 2 to the power of 2. So I'd have 2 to the power of 2. That's what I'm doing with this 4. And then I'm going to go ahead and copy 2x plus 2, and then times 2 to the power of x minus 1, to the power of 5, x plus 3, right? This allows me to have it in the same base. That means I have a power to a power. I'm going to go ahead and multiply in. So I would have 2 to the power of 4x plus 4. Still have the 2x minus 1 over the 2 to the 5x plus 3, like so. From here, I'm using the same rules that I had from above. So I'm going to go ahead and add these together. So I'd have 2 to the 4x plus 1x is 5x, and then 4 plus negative 1 be positive 3, and then still have my same denominator, 2 to 5x plus 3, like so. I can see these are the same, so right away I'm like, oh, this equals 1. If I needed to, I could also subtract them. So 5x minus 5x would be 0, 3 minus 3 would be 0, so 2 to the 0 power also equals 1. So you can see that playing out there. All right, so this is the first time we see, okay, I can actually take this 4 and turn it into something more useful for myself. We're going to apply that in this next one as well. Our final exponent rule is one we started with at the beginning of this video. So remember that if you have a denominator, if you have a fraction for your exponent, your denominator becomes the index, and you have a to the m there, right? This is our radical rule from above. So if I'm thinking about this one, I'm going to start by not thinking about the square root. Come back to the square root later. I'm going to simplify what's inside here first. So 3 to the power of 2x plus 2, how much I can do there. I can't automatically combine these because they don't have the same base. So I'm going to turn the 9 into 3 squared. I still have the x minus 4 from before. So this is 3 to the power of 2x minus 8, like so. And then I also have 3 to the 2x plus 2 is still here. Now that they have the same base, I can now combine them. So I have 3 to the 2x plus 2x would be 4x. 2 plus negative 8 would be negative 6. And this is still square rooted, right? At every point along the way, it was square rooted. So now I'm thinking, okay, my square root, I know this is a 2. There's technically like a 1 here. right? Or I could be thinking, okay, this is my exponent. I have a 2 here. So this 2 is going to swing down here to be my denominator, right? So I would have 3 to the power of 4x minus 6 over 2. And I can simplify this fraction. So I have 4x over 2 would be 2x, minus 6 over 2 would be 3. Like that. So I could have this answer here. If this seems complicated to you, you can do the exact same thing. You can say, okay, I have 3 to the 4x minus 6, and I know that a square root is like a 1/2 power, right? A 1/2 power. That 1/2 power is going to get multiplied in here. 1/2 times 4x would be 2x. 1/2 times negative 6 would be negative 3 with a base of 3. So you get your exact same answer here. We've done a lot of similar rules to what you've already known, and then we had a lot of more complicated examples. So feel free to ask any questions you have, and I will see you in class. Thanks.